Okay, I'm re-recording the chemistry class from this morning because the recording got erased accidentally before I could post it. So I'm teaching to no one. My pace will be kind of different. So calculated concentrations of acid-base solutions. As it says, they're water equilibrium. Acids and bases are dissolved into water to form solutions that disturb an equilibrium of ions that already exists in water. Water equilibrium forms because water ionizes to a very small amount to form hydronium ions and hydroxide ions. Just look at this equation here. Two waters, one acts as an acid, one acts as a base, one donates an H plus. So you get an H3O plus forming and hydroxide. This happens very little, about 1 in a billion. But it does happen. But they're not to any great extent. You can't conduct electricity in water. But just to take a look at what we're talking about here. I've got this diagram here, and I'll show you. So you've got all these water molecules, and I'm representing them as HOH. But a few break apart. So here I have H3O plus. Here's a hydroxide down. Well, by random chance, sometimes collisions or whatever, another one will break apart. This might latch on. There become water. So this might break apart. Boom. You got another H2O. At the same time, this guy might drift, maybe form water over here. Remember the way equilibrium works. It's dynamic. Every time an H3O is formed and a hydroxide is formed, two of them disappear and become water again. So that's pretty steady. So with that equation there, we can come up with this equilibrium expression down here. Products over reactants, but the reactant was a pure liquid, so it doesn't appear in the K expression. So the concentration of hydronium ion times the concentration of hydroxide. Kw, just like we use KEQ, well, we're using a W just to say it's water, Kw. There we are. This equilibrium constant is labeled Kw. It's the value for pure water at 25 degrees Celsius. Assume you're using that Kw value for any problem I give you. And we usually have room temperature, 21 degrees, but we'll use this value. Here's a question for you. In a neutral solution of water, what's the concentration of hydronium ion and hydroxide ion? Well, we're going to use the Kw expression. But first, I think we should just, well, I'll write this out now. Just give me a second, I'll get up. We've got two waters. Oh, this is very interesting. I've got two waters. Very small extent, we've got hydronium ion, hydroxide. I'm going to do an ice chart. You don't need to do this every time. But let's just say, first of all, there's nothing because it's pure liquid, so we won't interact. But initially, I just have pure water 100%, just for thought. And the way this works is there's a 2-to-1 ratio with each of these. So if 50 of these disappear in nature, I'll use 22 of these break up, 22 water molecules break up. You're going to get 11 H3Os, 11 hydroxide. Same ratio when we're talking about moles. Well, we're going to use X. Imagine you had 2X moles in a liter of water break up into its ions. So you get a single X H3O, single X. I don't know. That happens to be X. They're the same amount. I'm going to use this Kw expression to solve this problem. In pure water, what's the concentration of hydronium, hydroxide? I'm going to substitute the K value. 1, 10 to the minus 4. From our ice chart above, I'm going to use X for the hydronium, X for the hydroxide. So that becomes X squared. Okay. The way to solve something like that is to do a square root. Square root of 1 on 10 to the minus 7 x. That almost solves the problem. We really were asking for hydronium ion concentration and hydroxide. But that's given by x, right? So it's the same number, but we'll put moles per liter. All right. So they're in the same amount, and that is extremely small. 1 times 10 to the minus 7, like, if I was to write this out, and I don't recommend it, I'll write this now. 1 times 10 to the minus 7 is 0.000000001. Anyways, that is tiny. The same as 1 times 10 to the minus. So we're going to keep that in mind as we look to the next page. So if you need to jot down notes, do this part of it. Calculating the concentration of hydronium ion, hydroxide ion for strong acids and bases. Strong acids are added to water, the H2O plus. The hydronium ion concentration in the solution would become equal to the concentration of hydronium produced from the dissolved acid, unless it was very dilute. The same is true for the hydroxide if you're adding a base. Now let's go back and just see why this is true. I guess we'll do this first. We'll go back and see. Consider adding 2 moles per liter of HCl to water. So here we are. I start with 2 moles per liter. And when I say strong acid or strong base, that means it's a one-way, not an equilibrium reaction. So I got the big fat arrow. It does not go back and forth. It goes 100%. This was a balance of 1 to 1. So we have 2 moles in a liter of water of HCl breaking up. We've got 2 moles hydronium ion. We also have 2 moles of chloride ion forming 2, but we're not there. What about the amount of H3O that was originally there then? Why does it just become 2 moles? Well, let's take a look back. You know why I wrote this out the long way? If you start out in water, you initially have this small amount of H3O, and I add 2 moles of HCl to that. Well, 2 moles of hydronium ion now. Take a look at this. Okay, we know significant digits tells us that we can do that very, very well. I mean, this is not, we're going to just keep it as 2. That 0.000001, I forget how many zeros it is. That doesn't really change it. It's 2. That's why we're doing what we're doing. And ignoring that there really was a very minute amount of hydronium ion. To answer this question, the first part is really simple. Strong acid, I guess I'll say, oh, write this down, because you will too. There's a strong acid. All of the HCl reacts 0 plus hydronium. And the chloride ion, I'll put that in. It doesn't affect this question. Therefore, what did I write down HCl? Wow. Therefore, the hydronium moles per liter. Now that answers one of the questions. You need the hydroxide. Well, to do that, we're going to use the K expression again. KW doing well. Hydronium times hydroxide concentration. We know two of these three things. We know Kw is always 1 times 10 minus 14. We know the hydronium ion from the above is 2 moles per liter. I'll leave out the units because we're talking within the calculation, but on the final answer. We want to solve for hydroxide. We do that by division. Hydroxide is when you do the division, find that oxide concentration is 5 times 10 minus. This makes sense. The hydronium, they were initially equal before you added the acid, but then the hydronium goes super high. The hydroxide goes super low. It's an acidic solution, very few base parts. What about base? I've got this one worked out, so I'm going to go over it with you ahead of time. Calculate the hydronium and hydroxide concentrations of solution. When you start with 4.5 grams of calcium hydroxide dissolved with 200 mils of water. Now, in this case, I didn't give you the moles per liter, the concentration of calcium hydroxide. So the first thing you should do is change that to moles and then find the concentration. 4.5 grams calcium hydroxide. Use periodic table, look up the mass of calcium, that's 2 O's plus 2 H's, that's 74.10. Do the calculation and you get it. 0.061 moles calcium hydroxide. I put 60 and then a small 7. Just because I'm going to carry that extra digit through the calculation. I use a small one to remind me there's only 2 significant. Once I have the moles, I need to divide by the liters. 300 mils is 0.3. Do that. Now I cut down to 0.20 moles per liter. That's the calcium hydroxide concentration. Now this is more like the previous acid problem. I've got the moles per liter, the concentration of the base. We need a reaction number. And this is, we call this an Arrhenius base. It's calcium hydroxide. If you have hydroxides, don't worry about adding them to water. Just break them up into the ions. Look them up on the ion chart if you need to chart. Calcium hydroxide, solid, added to water. Calcium ions, 2 plus, 2 groups of hydroxide. This is important. This is the one thing. 2 ratio. That means if 5 of these calcium hydroxides were to break up into its ions, we have 10 hydroxides formed. So, we start with, as we figured out, decimal 20 moles in a liter of water for calcium hydroxide. And it breaks up. Okay. Twice as much, so we multiply the hydroxide. That's decimal 40, 4/10 of a mole per liter. I'm going pretty fast, so you might pause the video. Now we figured out the hydroxide. Time to figure out the hydronium. Again, Kw expression, sub in 10 to the minus 14 on the left, sub in the hydroxide concentration we found, and just isolate for H3O. Calculator. After you do a couple of these, you might notice whenever you're using this Kw formula, since Kw we're always going to use 10 to the minus 14, it just turns out to go from hydronium to hydroxide or vice versa. It's always just 10 to the minus 14 divided by the value you know. That gives you the other thing. Now I'm saying if you have hydroxide, you divide by hydroxide, you get hydronium. If you have hydronium ion, you divide by that, 10 to the minus 14. Hydroxide. Now, towards the end of the class, I left off with some questions for people to do. I'm going to just jot them down and try them. I have the answers off to the right. Make sure you're doing them. 1, 2, pause that. Here's the answers for 2. There is 3. Good.